Thank you all for coming. First of all, it's a real honor to be able to present this workshop. Thank you to Matthew for the wonderful talk about mere time. So my name is Dr Bezuidenhout. I'm a postdoc here at Northwest University. I did my PhD work under the MERTA project, which is carrying out real-time and continuous search for fast radio transients with Meerkat. So that includes sources like Pulsars, but predominantly that's all about fast radio bursts. So my real passion is fast radio bursts, but also will admit to having a soft spot for Pulsars. So I hope that my talk I'm able to convince you a little bit that Pulsars are definitely worth studying. With my talk, I wanted to ask two questions. The first is what is a pulsar, and then secondly, how do we find it? So, for the first question, Matthew has already covered a fair bit of that territory, but if you didn't understand it the first time with an Australian accent, you'll get a second shot for the proper South African. Let's see how we go. I'm a bit sad this week. This university is hosting a forum on the use of AI in academia. That's on Wednesday. I'm a bit sad I'm not going to be able to attend this workshop. So I thought to console myself, I will incorporate a bit of that into my talk. So I asked the question to ChatGPT, what is a pulsar? I was actually pretty pleasantly surprised that I gave a really good answer. It said a pulsar is a highly magnetized, rapidly rotating neutron star in beams of electromagnetic radiation, including radio waves, with regular and precise pulsing pattern. So, for one sentence definition of a pulsar, it's about as good as you're going to get, but it is a mouthful. So, let's go through that bit by bit. The first thing that we learn from that definition is that pulsars are neutron stars. So what is a neutron star? A neutron star is one of the end stages of the star's life cycle. I got this really handy graph from Wikipedia, and it shows all the different branches that a star can take along its evolution lifetime. Stars, as we know, start out as a molecular cloud that very slowly over many years coalesces, comes together due to the pull of gravity, starts heating up. Once it gets hot enough, thermonuclear reactions start happening. The hydrogen starts fusing into helium atoms, and it's burns that its hydrogen converts into helium that releases energy. And that is what sustains the star against gravitational collapse. That burning can continue for millions, billions, trillions of years. That's what we call the main sequence. But at some point, inevitably, it runs out of hydrogen. At that point, it turns into a red giant, and it starts burning its hydrogen, converting that into carbon. Carbon gets fused into oxygen, and so on, building heavier and heavier elements in the core until you get a core that's made up of iron. And the thing about iron is that the fusion reaction is endothermic, so to make that happen you would have to put energy into the system rather than getting it out. So the fusion reaction stops, the star stops burning. And then what happens at that point is dependent on the mass of the star. So for low mass stars like our Sun, it explodes in planetary nebula, and then what's left over is a white dwarf. So that's a very compact star that is sustained by electron degeneracy pressure. So that means that the only pressure that's keeping the star up is that due to the Pauli exclusion principle, which states that electrons cannot occupy the same state. If the progenitor star is very massive, it's greater than about 8 times the mass of our Sun, and the gravitational collapse is so forceful that it gets past even that pressure, and there's a neutron star that is sustained by neutron degeneracy pressure. If the star is very, very massive, greater than about 40 times the mass of our Sun, it collapses even past the neutron degeneracy, and you get a singularity before of a black hole. So a neutron star is just about the densest material that you can get in the universe without going all the way down to the black hole. So what you get with a neutron star is something of the mass about 1.4 times the mass of our Sun, compressed down to a diameter of about 20 kilometers. And the density of that is such that if you take a tablespoon of ground of the Earth, that weighs about 20 grams. If you take a tablespoon of material of the Sun, that would weigh about 2 kilograms. If you take a tablespoon of a neutron star, that would weigh as much as Mount Everest. So that tells you the kind of physics that is involved in these systems. The second fact about them is that pulsars are highly magnetized and that they rotate rapidly. So during the supernova collapse, you go from a star which might have a radius of 1 million kilometers down to a radius of 10 kilometers, and the angular momentum is conserved using following that equation, meaning that you get a factor 10 to the power 10 speed up to it. That means that for a star like our Sun, which rotates once every month or so, you get, and you would get a neutron star that spins once every second or so. Then you get millisecond pulsars, as Mechiel explained, which gets spun up even quicker, up to a millisecond or so by a heating binary quantum. You get periods up to 76 seconds is the longest spin period that we have measured so far. There are different theories for how what determines the final spin period of the pulsar. Just as the angular momentum of the pulsar is conserved during collapse, so its magnetic flux is also conserved. So you also get a factor 10 to the power 10 amplification of its magnetic field. So to give you some indication, the Earth has a magnetic field with a strength of about 10 to the minus 4 Tesla. The Sun is about twice that strength. The strongest man-made magnet ever, I looked this up, it weighs 35 tons and it costs $14 million to make, and it has a strength of 45 Tesla. The neutron star with the strongest magnetic field that we've ever seen has a magnetic field of 1.6 billion Tesla. To give you an idea. To be fair, most pulsars have a magnetic field closer to about 100 million Tesla, but that's still pretty strong. So it's the combination of these two facts, the rapid rotation on an extremely strong magnetic field that leads to the next trait of the pulsar, which is that emits beams of electromagnetic radiation. So understanding how pulsars actually emit radiation is a really complicated topic. It's still a hot topic of research to this day. There's very many theories about too many conclusive answers. But we are able to sketch out a rough idea for how this basically works, which is shown by this model, which depicts what we call the rotating dipole model of pulsars. So we have a neutron star in the center, surrounded by this magnetic field, shown by these lines, and the rotation of the magnetic field together with the pulsar induces an electric field. And that electric field is so strong that it's able to pull charged particles from the surface of the neutron star and accelerate them along these magnetic field lines. So in this region where you have a closed magnetic field, that region is filled up with these particles. It creates a plasma that is co-rotating with the neutron star. And because the magnetic field is frozen into this co-rotating plasma, that creates a torque on the magnetic field that slows the pulsar down, and that energy that's lost due to magnetic braking must be expended by accelerated particles along the open field lines. So you get particles that are accelerated to relativistic velocities out along these magnetic field lines. And then they cause a big cascade, a particle cascade that ultimately produces synchrotron radiation that is beamed along the magnetic fields of magnetic poles of the neutron star. So that's the basic idea. In reality, it's a much more complicated question. Chris knows a lot more about this than I do, so if you have any questions about that, directly to him. But the next, the final part of the puzzle for what is a pulsar is that it produces a regular and precise pulsing pattern. So because the magnetic field, the magnetic axis of the neutron star is offset from the spin axis, as the neutron star is spinning, the beams rotate with it. So if you're an observer on Earth, what you see is when the beam of the pulsar sweeps across your line of sight once every rotation. So the way the pulsars are observed on Earth is as this regular blip of the radio emission once every rotation of the neutron star. So this is what pulsar data looks like. On the left you get what we call a single pulse stack. So each of these lines correspond to one rotation of the pulsar, with the amplitude of the line indicating the intensity that you measure. And you'll notice that each pulse is slightly different for this pulsar, but if we add together those pulses over a single period of time, we call the integrated pulse. That's the average pulse of the pulsar. And on the right we have a gallery of different integrated pulses for different pulsars. And you can see that there is a variety of different shapes that we can get for pulsars. Some have single peaks, some have double peaks. There are any variety of different behaviors. And each pulsar has its own unique profile that is kind of its fingerprint. Once you get to know a pulsar, you sort of start to recognize these shapes like their names. And what determines the shape of this profile is down to a couple of things. But mainly it is down to geometry, so it depends mostly on how the magnetic axis is offset from the spin axis, and then also the angle at which we are observing this rotation. So what we can also do with these integrated pulses is to use them to make a timing model of the pulsar. So that's what you will learn all about during this workshop, is that you use that integrated profile to make a timing model which predicts to very high precision the exact time when the next pulse in the series will arrive. And what goes into that model is a bunch of different parameters, but the two most important ones are the period of the pulsar, so how often does it rotate, know those two parameters of the pulsar, you can place it on a plot like this with a PP dot diagram. This is the most well-known primary plot that plots out different pulsar populations. And what you can see is that that they emerge different clusters on this plot corresponding to different subpopulations of pulsars. So at the center there, we have this big blob that basically corresponds to your carbon garden variety pulsar, canonical pulsars. Then you have a cluster down on the bottom left corner. These are your millisecond pulsars, maybe explained. Up at the top right, you get magnetars, which are especially magnetic pulsars whose exact origin and characteristics are still debated. You also get a population of RATs, reflecting radio transit, with blue triangles, and these are intermittent pulsars, so they don't emit the pulse from every rotation of the neutron star. And you can work out, using some simplifying equations, you can work out using the period derivative, some basic traits of the pulsar just based on those two parameters. So you can work out the rate at which the neutron star is losing energy, the E dot. You can also get an estimate for the age of the pulsar. Reiterate, it's not a measurement, it's just an estimate. It could be wrong in many different ways. And you also get an estimate for the magnetic field at the surface of the neutron star. And since they depend only on P and E dot, you can make these lines, draw these lines on the PP dot diagram, where these diagonal lines going up from left to right, they correspond to lines of equal age from 1 kilo year up to 100 gigayears. So broadly, as you go down in this plot, the pulsars are getting older. Then these diagonal lines going down from left to right, they correspond to the magnetic field from 10 to the 15 Gauss down to 10 to the 8 Gauss. So going up in this plot, the pulsars are getting stronger in magnetic field. Obviously, the magnetons have the strongest magnetic fields. So, in terms of numbers that we found so far, Matthew said we had 3,500 radio pulsars. I say 3,000. So I think we can compromise and say 3,250. We also found about 120 RATs. And only about 13. So that's my answer to the question of what is a pulsar. Perhaps before we move on to the next bit of how we define pulsars, we should have to stop and see if there are any questions about this so far. Yes.
So just on the previous slide, that plot. That upward line. I can't see exactly what it says. Could you maybe elaborate on what that is?
Yeah, so that says depth line. So that's one model for what we call the pulsar depth line, which is the idea that beyond a certain point, pulsar should not be able to produce any radio emission. So basically, the K cascade process that produces emissions ceases beyond a certain point. That's one model. As you can see, there are some pulsars beyond that point, so obviously it's not a rock solid theory, but there are different models for different depth lines, and often one of the major ways that we study the energetics of pulsars is to try to find this depth. Because that tells you a lot about how this emission actually is produced. Any other questions? No? We're all comfortable with what also on now. So let's move on to the next question. We know what also is, how do we find them? So the diagram that I have up on the screen here is shows all the different steps that goes into finding also all the way from maybe raw data files to possibly maybe hopefully crossing fingers finding pulsar. As you can see, it's a long and tedious and arduous process. Really, it deserves its own workshop. So I'm not going to go into this with any detail, but I want to convey some of the most important concepts there. And really, I want to make it clear that this is not a simple process of looking at the sky and seeing a pulsar. In reality, we have to look at the data and actively hunt for the signals of these things. So, what we typically start with is something called the time series, meaning the telescope is pointing in some direction, looking at some point in the sky, and it's making a measurement of the intensity of the radio emission at that point in the sky. And if you're doing a pulsar observation, Meerkat is taking that observation once every couple of microseconds or whatever it is. And so you end up with a time series like this one. And our task then is to find in this time series what looks like random noise, the signatures of the periodic emissions of pulsars. So that sounds easier than it is for one reason, because the signal of the pulsar travels a long way to get here, and on the way it gets distorted. So Matthew already talked about the dispersion of the signal, but I'll just say it again, because why not? So that as the pulsar travels to us, it moves through the interstellar medium. The index of refraction that it experiences is dependent on the frequency of the emission. So the high frequency elements of the emission arrive earlier than the later ones, the high frequency ones. And you get a delay in the arrival time of the pulse that is dependent on the frequency to -3. So the degree to which that signal is dispersed is quantified by the dispersion measure. And that's a measurement of how many electrons are between us and the source. So if we want to find a pulsar, the signal doesn't arrive all at once. We have to correct for that dispersive delay. But if we don't know anything about the pulsar, we don't know its dispersion measure. So what do? We have to assume a series of trial dispersion measures. So we say, let's look from a value of 0 to a value of 1,000 or whatever, and we're going to use X number of trials in between that. And then for each of those dispersion measure trials, you have to carry out your pulsar search. So when you're designing a search for pulsars, you have to be very clever with how you devise your dispersion measure trial strategy. If you use too few trials, too coarse of a search, you stand a chance of missing a pulsar with a dispersion measure between two trials. But with every trial that you add processing time, another factor of processing time. So once we have our de-dispersion trials, for each of them, we de-disperse the time series, and then we apply a Fourier transform. So hopefully you have learned about Fourier transforms before, but in broad terms, what this does is decomposes the signal into a sum of sines and cosines with different phases and amplitudes. And if you then plot the spectrum of those amplitudes, you get something like this. And each peak in the amplitude spectrum it corresponds to some periodic signal within your time series. So you can do that for one instance of time. If you then average that over an extended observation, you can make an average spectrum. The more that you observe, the neater that spectrum will be. So the flat horizontal portion is called white noise, which just means that all frequencies are present in the signal to equal measure. Down at the bottom of the spectrum, below 10 Hz, you get what's called 1/f noise. So that's a noise term that is present in any amplitude spectrum that you will see. Usually we just subtract that. And then you see spikes at 13 Hz, 26 Hz, 39 Hz, and 60 Hz in this case. So 60 Hz is a bit conspicuous because that is, in South Africa, that's the frequency of alternating current, so that indicates that probably in this signal is interference into alternating current. Then there's these three peaks, 13, 26, and 29, so that's multiples of 13. So 13 Hz in this case is what we call the fundamental frequency. That is the frequency that's connected to some physical process. In this case, that would be a pulsar repeating 13 times a second. And then you have multiples repeated multiples of this fundamental frequency. Those are called harmonics or aliases of the fundamental frequency. And those are caused by the fact that we are using a discrete Fourier function that samples the time series at a rate below the Nyquist frequency. So those are just a matter of life, you have to deal with them. One thing that you can do to increase your sensitivity to this periodic signal is because the power of the signal is spread out across its harmonics, you can do something called incoherent harmonic summing, which means that you basically stretch out the spectrum and add it to itself in such a way that you're basically adding together all the different harmonics. And that gives you a boost in your signal to noise. I think that amounts to about the square root of 2. So once you've done that, and you've identified all the fundamental frequency candidates, you end up with a list of candidates. Could be hundreds of, tens of thousands of candidates long, depending on your research and your VM trials. And each candidate then has a candidate period, a DM, and a signal to noise ratio. And then you have to go back for each of those candidates. You have to refold your original time series, and then try to figure out if for each candidate classified whether it's a real pulse or signal, or whether it's corresponding to some noise or interference in the system. So you can make plots like these. These are examples of candidate plots from Presto, which is a popular Pulsar searching software package. And for each of these candidate plots, you'll then have to classify it. Either you can do that by eye if you have a lot of time, or hopefully you have some sort of machine learning classifier that can do that for you. So that's the basic process for isolated pulsars. If you have pulsars that are in binary, the process is a little bit more complicated because of the fact that depending on where your pulsar is in its orbit, the apparent period of the pulsation will be different. So in your spectrum, instead of getting a nice neat peak corresponding to the fifth frequency, you get one that's kind of smeared out. and so you lose a lot of sensitivity in the signal. So to correct for this, we do something called acceleration searches, which means that basically you assume some value of acceleration of the pulsar, and then stretch or compress the time series to compensate for that. So on the right, that shows what it looks like before applying the acceleration search, and once you've corrected the correct acceleration. So you have to do this for, again, a trial, a series of acceleration trials. So if you are trying to do an acceleration search, you're trying to look for binary pulsars, this increases your processing time corresponding to how many acceleration trials you have. So what I've described so far is one option to find pulsars. It is not the only way to find pulsars, and it does have a significant drawback, or really two drawbacks. The first is that obviously it's not very sensitive to pulsars that don't emit regularly. So RADs, which emit very frequently sometimes, they are very difficult to find using this kind of Fourier transform-based periodicity search. Additionally, this Fourier transform-based search is inherently less sensitive to pulsars that repeat slowly, to long period pulsars. Why? If you look at the amplitude spectrum I showed you, if you have a very long spin period, the spin frequency is very small, right? And it could be for very long period pulsars greater than about 10 seconds, that the fundamental frequency is actually given in this 1/8 noise, and you're just getting rid of it and losing a lot of the signal. Additionally, if you're doing incoherent harmonic summing, there's a limit to the amount of harmonics that you're actually able to add together. Whereas the signal itself might be spread out over any number of harmonics, and so you inherently lose some sensitivity by adding together a finite amount of harmonics. So the vast majority of pulsars that we have found have been found using these periodicity searches, but in recent times people have been kind of reconsidering all this in the light of a few discoveries of pulsars with very long spin periods, longer than we have previously thought possible. So just last year, I think it was that we found this pulsar with a spin period of 76 seconds, and that pulsar has prompted a lot of research because it fell below the deadline that we talked about in a lot of places. So people are really interested in finding these very long period pulsars because they're really useful in training our ambition. So as an alternative to the Fourier transform-based searches, there's something called fast folding algorithms, which is basically a brute force approach to a periodicity search. So instead of taking a Fourier transform, you simply have a series of DM trials, and then you have a series of periodicity trials, and you fold the time series for each of the, according to each of the periodicity trials, and then try to see what combination of DM and period maximizes the signal-to-noise ratio of the signal. So that's it's a very simple approach, but it is very computationally expensive. And it is only recently that it's actually become possible computationally to carry out these fast folding searches, and a couple of telescopes have now been incorporated these into the pipelines. There's also another alternative, which is called single pulse searching, which is not a periodicity search at all. You completely ignore the prospect of the sources repeating periodically, and you simply look for spikes in the time series. So you take the time series as it is, and you involve it with a series of box-core filters, these rectangular functions with varying widths. And if there's a spike corresponding that equals the width of the box-core filter, it will have a high signal-to-noise ratio. So we're trying to find signals that maximize the signal-to-noise ratio as a particular width increment. So again, it's a simple algorithm, and it is very computationally expensive. This kind of search has really only recently gained prominence because people have been using this to search for fast radio bursts, which are these millisecond duration bursts coming from outside of the galaxy, whose origins are still very uncertain, and people are still hotly debating that. And because these signals, unlike pulsar signals, are not periodic, we have to use single pulse searches to find them. And so people have been carrying out these kinds of single pulse searches, and in the process happening to find some pulsars, including with very long periods. So that's where the project that I'm working with is carrying out this kind of single pulse search primarily for pulse radio bursts, but we have also found a couple of pulsars using the same method. So that covers the software side, the algorithmic side of how we find pulsars. But you might also ask, well, what about the hardware side? What kind of telescopes do we need to find pulsars? So the vast majority of pulsars that we have found so far have been found using these big single-dish radio telescopes in various countries. I put together a tally of all the pulsars found using different telescopes. These numbers are just from what I got from the Pulsar catalog, so if they're not up to date or whatever, don't shoot me, which is what I was able to find. But what's certain is that the telescope that has found by far the most pulsars is the William telescope in New South Wales in Australia, also previously called Parkes telescope. That has found more than 1,400 pulsars. Most of them, more than 800 of them, it's found with multi-beam survey, so it's a single dish with a single receiver, but it has multiple feed horns, so you're able to form multiple beams on sky, and it means that you have a big field of view, and that maximizes your ability on pulsars. In second place at the moment is still the Arecibo telescope in Puerto Rico, which you might remember from a few years ago, the receiver came crashing down and broke the telescope, so rest in peace Arecibo. It's not going to be making any pulsar discoveries soon, unfortunately. In third place is Green Bank telescope in the US, and then FAST telescope in China. It's the 500-meter telescope, the biggest single-dish radio telescope in the world. That's already found 262 pulsars. It's only been active, I think, 2 years or so. And then finally, if my accounting is correct, I believe officially Medtech has now moved into 5th place on the leaderboard through the TRAPM collaboration, which is looking for pulsars with Meerkat. And as Meerkat continues to observe, we will surely find more of these. You might notice that Meerkat is the only array telescope on this list. That is mostly due to the fact that these single-dish telescopes, Maria and so on, they've been observing for a much longer period of time, so they've had more time to discover pulsars. Whereas FAST and Meerkat have only come online recently. But in fact, array telescopes like Meerkat have a significant advantage in finding pulsars. Why is that? That comes down to the sort of collecting capacity of a single dish compared to array telescopes. So for a single dish telescope, the gain of the telescope, which is proportional to the sensitivity, is proportional to the area of the connecting surface. So if you want to have the most sensitive radio telescope, you build a huge dish. But at the same time, the field of view of the telescope, meaning the area of the sky that is able to observe at any given moment, is inversely proportional to the diameter of the dish. So the bigger that you build the dish, the more sensitive it is, like the smaller the part of the sky that you can see at any given moment. So if you're doing an untargeted search for pulsars, if you want to look at the whole sky and find pulsars, it takes much longer to do that with a single dish radio telescope. On the other hand, for the radio telescope, the gain is proportional to the number of the dishes that you have. So it's basically the sum of the gain of all those individual telescopes. But the size of the beams is inversely proportional now to the maximum baseline of the array. So that's the furthest distance apart between the antennas that you're using, meaning that the size of any single beam is very small. You have a maximum baseline of a couple of kilometers. You get a very small beam, the order of tens of arc seconds. But the advantage that we have is that we are able, by manipulating the arrival times or the delay corrections that we apply to make these beams, we can focus any number of hundreds of them at any points across the sky to form tide array beams like this, which are arranged in pattern. And if we tile these tide array beams, we can cover a large part of the sky. And the area of the sky that we are able to tile is inversely proportional to the size of one of these telescopes. And because you're using smaller telescopes which look at only 1.3 meters, the area of the sky that we're able to cover with these beams is much larger and is accessible to a single dish telescope. So that's the advantage that we have for finding pulsars with communicate. In 2015, Keane et al. Put out a paper projecting what would be our prospects of finding pulsars with SKA. And they predicted that using, for the SKA phase 1 in South Africa, we will be able to find about 7,000 canonical pulsars, as well as about 900 millisecond pulsars. Whereas for the full stage 2 SKA, we should be able to find anywhere between 24,000 and 15,000 pulsars. So it's looking very likely in the coming SKA future there's going to be a real boom in the number of pulsars that we find. The real limiting factor in the degree to which we can capitalize on this is going to be whether we are able to create the processing infrastructure to find all of these pulsars, and whether we're going to have the people power to actually do all this work. So it is very important for the coming era that we create pulsar astronomers who are able to take advantage of all this data. And that's why I think it's really important workshops like this to inspire, hopefully, some of you to become part of this pulsar revolution. That's it from me. Thank you.
Next questions for Jan. forming algorithm to find pulsars. How do you decide on your periodicities?
Yeah, so it's another one of those balancing acts. So first of all, you want to decide on your limits. So usually you go down to say, we don't want to look anything smaller than a millisecond. That would be your lower limit. And then maybe you need to take an upper limit of, let's say, 100 seconds. And then what determines how many trials you can have in between that is how much processing power you have to your disposal. So you have to work out how many trials am I going to be able to do while still making this a reasonable or a doable exercise. There's no hard limit, it's really just how much processing power you have.
Yes, so the other one, it's a bit more interesting. So you see, so for a single dish, you have a smaller beam that you can see through. Now, in some cases, if we consider like satellites and stuff that orbit the Earth, is a smaller beam not more accurate because you don't have that much, noise or disturbances of satellites that passes through the area which are really noise that very concerned.
Yeah, so that's an interesting question. Is the problem of interference a greater problem for a ray telescope that have a larger field of view? That theory is not in this game.
Yeah, so the side lobe pattern, the area formula is lambda over d, or 1.22 lambda over d. So with a 14-meter dish, you've got about a degree on the sky for your primary lobe. For something like parks, it's only like 15 minutes. So the rate of decay of the side lobes is very extreme. Unfortunately, it means for something like Meerkat, you see the satellites everywhere. And so that's a disadvantage. The advantage is that you're actually looking at more sky. But then you've got a computational burden of having to synthesize all the what's called the tide beams, and so it's an interesting tension. Whether you prefer to have like little dishes that look at a large amount of the sky, but then the satellites are worse. So you might remember I was talking about my mobile phone that's half a watt. So a Jansky is 10 to the minus 26 watts. And the typical pulsar you find these days is like 0.1 millijansons. So a mobile phone only needs to be within like 100 kilometers before it's much brighter than the brightest pulsar in the sky, even though it's attenuated by the side lobes by like a factor of a million, which is kind of grim. And then the GPS satellites are super bright. So they're even worse.
Yeah, that's true. I'll just add my personal experience when we started out using Meerkat to look for Australia bursts. Before we had any clever way of dealing with it, RFI used to take out probably 40% of the bandwidth that we were able to use. It was just so bad. So we spent ages just coming up with solutions for how to deal with that interference. But at the moment, I mean, we have developed pretty smart solutions for that are able to basically in real time remove much of that interference. But yeah, it's a challenge. It's what Meerkat is a pathfinder project for SKA. So one of the ideas is that we figure out this stuff and learn how to deal with these massive data rates and things that come with the telescope, like the SKA. So we figured out a lot of clever ways to make it better, but still it's a big challenge. Yes.
I was just wondering, is there some reason behind the expectation for the distribution of how many pulsars will find will be millisecond pulsars? Is there some kind of physical mechanism explaining that?
I mean, I think that just comes down to birth rates that we expect for millisecond pulsars, right? So only some proportion of them go through that process of dying or being spun up by binary pulsar. So I don't know in detail how they made that calculation. It's just probably looking at the proportion of millisecond pulsars that exist and projecting them.
It's based on the luminosity function of the known populations and then extrapolating it down.
Yeah.
So if you plot log n versus log s has a certain slope, and you can sort of go, oh, the little telescope 10 times bigger, then I should find 30 times more pulsars. And in fact, if the SKA is 4 times better than Meerkat, then you should find 8 times as many pulsars with the SKA as with Meerkat for the same integration time, if the population is uniformly distributed in space.
And then the population of those that are millisecond pulsars, is that also just extrapolated from what the distribution is now?
Yeah, so it used to be that it used to cost an absolute fortune to even be able to sample the data at like a millisecond. So when the initial pulsar surveys were done, they used to sample at 20 milliseconds. And then as we got more and more money and better and better technology, we keep ramping up the sampling time until now we do typically like 64 microseconds. And unfortunately that leads to a sampling time squared penalty on the computation side. Computers are actually getting faster than the sampling time can go. So, but it's still the case that radio waves that scatter are the interstellar medium, and no amount of signal processing can save you from that. Once the radio waves are scattered by one period,